Hi guys, so today we're going to talk about adding and subtracting radical expressions. I think you guys are going to like this. It's going to be quick and nice to us, so let's get started. Okay, so when you're adding and subtracting radical expressions, the key thing to remember is that you can't simply just combine the radicands. You have to simplify and combine like terms, and what do I mean by like terms? Well, each of your radical expressions has to have the same index and the same radicand. And if they have the same index and the same radicand, then you can combine them by either adding or subtracting. But if they don't have the same index and the same radicand, you might have to just do a little bit of work to get them to have those things in common. So, for example, we're going to go to a really basic example here, okay? Let's say I have 2 oranges and I'm adding 3 oranges, right? So 2 oranges plus 3 oranges would give me 5 oranges in all. Same thing with x's. 2 x's plus 3 x's gives me 5 x's, right? Well, when we think about radicals, it's sort of the same thing. 2 cube roots of 7 plus 3 cube roots of 7 equals 5 cube roots of 7, all right? And that's why it's so important that the index and the radicand are the same, because you have to be combining the same thing. In the first example, we were combining oranges. In the second example, we are combining x's. And in the last example, we're combining cube roots of 7, okay? I can take 2 cube roots of 7 and put 3 more cube roots of 7 with them, and I'll have 5 cube roots of 7. But if this had been 2 cube roots of 7 plus 3 cube roots of 5, well, those are 2 different things, and I can't just combine them together. So let's take a look at some examples. So here's our first example. The directions say subtract. So we have 7 square roots of 3x minus 5 square roots of 3x. So the first question I'm going to ask myself is the index the same and is the radicand the same? Because if they are, then I can just do a straight subtraction of like terms here. So that would make it really easy. So let's check it out. So our index here is that little invisible 2. This has an index of 2, right? This is a square root. So both of these expressions, 7 square roots of 3x and 5 square roots of 3x, both have the index 2. So far, my index is the same, so we're good. Now we need to check to see if our radicand is the same. And remember, the radicand is just whatever is underneath the radical. So 3x and 3x. My radicand is the same. Okay, so I can just do this as a straight subtraction. And just like that example where I had 2 oranges plus 3 oranges, here I have, and that gave me 5 oranges. Here I have 7 square roots of 3x minus 5 square roots of 3x. So how many square roots of 3x do I have left, you guys? 2. Okay, and that's indeed the answer. So when the index and the radicand are the same, it's just a straight add or subtract, which is really nice. But what if they're not? So let's take a quick look at an example where they're not exactly the same. We might have to do just a little teeny bit of simplification work first, and then we add or subtract. Okay, here's our second example. These directions say to add the square root of 18 plus the square root of 50. And I'm going to ask myself that same question. Is the index the same and is the radicand the same for both of these terms? Because if they are, then I can just combine them, right? So let's start with the index. I look here and we're dealing with square roots, which means we have that little invisible 2 again for both of these. So the index, it is indeed the same. Now let's shift our focus to the radicand, which is just everything under the radical. Well, in my first expression I have 18, and in my second expression I have 50. So my radicands are different. They are not the same, which just means I'm going to have to do just a tiny bit of work in order to make this happen for me. So what am I going to do? I'm just going to simplify the expressions, and we already know how to do this, okay? So I'm going to take these radicands and I'm going to break them down into their prime factorizations. So let's start with 18. You can start with any 2 factors of 18, and the first factors that pop into my head are 3 and 6. Well, 3 is prime, but 6 is not. So now I need to break that down into its prime factorization, and I think of 3 times 2. And now everything at the bottom of my factor tree is prime, so there's my prime factorization of 18, okay? And I also need to break down 50. So let's look at 50. I can do any two factors, it won't matter. So 5 and 10 come into my head. I know 5 is prime, so that I'm not going to break that down any further. And then two factors of 10, I think of 5 and 2, and those are both prime. All right, so now I'm just going to rewrite my expressions here. So I know that the square root of 18 is equal to 2 times 3 times 3. And how do I know that? Well, that's just the factors that I was given, right? 2 times 3 times 3, 2 times 3 times 3. All right? And I know that the square root of 50 is equal to 2 times 5 times 5, right? 2 times 5 times 5. That's why I did those factor trees. And since I'm simplifying radicals, I know that I'm looking for copies that I can pull out. So my index, like we said, for both of these expressions is 2, which means I'm looking for anything that I have 2 copies of, because I know that 2 copies on the inside is 1 copy on the outside, right? The first expression, the square root of 18, we broke it down to 2 times 3 times 3. Are there any factors in there that appear twice? Well, yes, I have 2 copies of the 3. So I can pull those 2 copies out, right? 2 copies on the inside equals 1 copy on the outside. So 2 copies of 3 inside the radical will give me 1 copy of 3 on the outside. Why? Because indexes and exponents are opposites. Opposite operations. They cancel each other out. If I have 2 copies of 3 on the inside, 3 squared, that radical, that square root, is going to cancel that out. So it just leaves me with 1 on the outside, all right? Which gives me the simplified expression of 3 square roots of 2. My 2 has to stay under here. I don't have another 2 to pull out with it, so it has to stay underneath the radical. But my 3 pulled out. So now let's look at the square root of 50 and use the same logic. My index is 2, which means I'm looking for any factor that I have 2 copies of underneath the radicand. I see I have a pair of 5s here. So 2 copies on the inside pulls out to 1 copy on the outside, which means that this simplifies to 5 square roots of 2. So now, you guys, the beauty of doing that is I can now combine like terms because my index and my radicand are the same. My index is still that 2, but now my radicand is exactly the same for both expressions. I have 2 underneath the radical. So I have 3 square roots of 2 plus 5 square roots of 2. And much like when we did 3 oranges plus 2 oranges, right, equals 5 oranges. Well, now we have 3 square roots of 2 plus 5 square roots of 2 gives us 8 square roots of 2. And that is indeed the answer. So it's really not that bad. There was just one extra step here where we had to take our radicands and just break them down into factors and simplify by pulling copies out. Okay, whatever our index is, that's how many copies we pull out, and that many copies on the inside equals 1 copy on the outside. Right? And then we just combined like terms like we did with the first example. So it's not that bad. It's a little extra work, but the more you do these, guys, you're gonna get so quick with them, so quick. So here's some examples for you guys to try on your own. Write each one on a piece of paper. Try them by yourself. If you need to, go back to the beginning of the video. Pause as you need to. As I do a step in the video, you do a step on your problem, okay? I know you can do it. Have fun. Reach out with any questions and just let me know, okay? Bye.